Hi, my name is Mitchell Sheep, and I'll be presenting Vertex coloring and numbers. Vertex coloring is the coloring of vertices or nodes on a graph in order to identify every node. One can imagine that coloring is a form of labeling like 1, 2, 3, 4, 5, etc., such that any vertex or edge of a graph is unique or different, which can be defined in and also can be defined in mathematical terms. A vertex K coloring for k element of positive integer is a function of f where the set of vertices is 1, 2, 3 all the way to k for all x and y element vertices of the graph G. Whenever a pair x and y is element of a set of edges, f of the function of x does not equal the function of y. This means that no edge should connect the same color vertex from V of G, which is a graph G set of vertices, and E of G, which is the set of edges for both for the graph of G. Chromatic numbers take a vertex coloring a step further. Chromatic number of a graph G is denoted by gamma of G is the smallest possible positive integer k such that G is a vertex k colorable and thus a good vertex coloring. The concept of vertex coloring falls into graph coloring, which is part of graph theory and discrete mathematics, which is part of mathematical structures that are fundamentally discrete instead of continuous like calculus or Euclidean geometry. The concept has several applications in map coloring, scheduling, preparing timetables, assignment, conflict resolution, and Sudoku. Fun game too. Vertex coloring was introduced as the as a front for graph coloring, as most graph coloring problems can be transitioned into vertex. For instance, edge coloring of a graph G is just a vertex coloring of its line graph, or the undirected set of adjacencies between edges. Face coloring of a plane graph G is just vertex coloring of its dual graph, which is the vertex of every face of G and edges whenever two faces are separated by an edge. Important graphs have predetermined chromatic formulas for determining the gamma of G, or the graph. Here's an example of a coloring. Stupid glare. And the table for G can be read as follows. A complete graph K of n has a gamma of n. So for any n vertices, it will take n colors to make n colors to complete the chromatic number. Even cycle graphs, which are cycle graphs that have an even number of nodes, such as a circle, square, triangle. These graphs are looked at as gamma of C2n equals 2. And cycle graphs, which is any odds, evens being like squares, hexagons, odds being triangles, pentagons, would have a chromatic number of 3. Complete bipartite graphs, which are K of RS, can be seen as gamma of KRS equals 2. Tree graphs are 2, path graphs 2, and null graphs are 1. Null graphs are just a bunch of nodes in space with no collecting lines, so therefore you'd only need one color. That's one of the only examples of that. Graph coloring came about in the need for map coloring or for maps and the purpose of quick identification of territories on a planar map with contiguous regions. While trying to color maps of English countries, Francis Gauthier postulated that four-color conjecture, which notes 4 colors are sufficient to color a map so that no regions share a common border with the same color. Gauthier's brother was able to pass along the postulate to his professor, Augustus de Morgan, at the University College in London. He would mention it in a letter to William Hamilton in 1852, the creator of the Hamilton cycle. However, it was dismissed. It was brought up in a meeting by Arthur Cayley of London London Mathematical Society in 1879. In the same year, Alfred Kempe published his paper that claimed a result of the postulate, solving it for nearly a decade. However, it was pointed out by Haywood that Kemp's solution to the postulate was wrong, and in the same paper he proved the five-color postulate, which is a proof that says it takes only 5 colors to color a map of counties, countries, territories. Saying that the planar map could be colored with no more than 5 colors, based on those ideas of Kemp. Following the events of Haywood, the passing of the next century saw many theories and a vast amount of work to reduce this number to 4. The 4-color theorem finally was proven in 1976 by Kenneth Appel and Wolfgang Haken. The proof mostly disregarded new developments and went back to works of Haywood and Kemp, and became the first computer-aided proof helping to define the computer science and furtherment of mathematics in the discrete field of graph theory. In the interim time, a man by the name of George David Birkhoff introduced the chromatic polynomial to study the problems of coloring and was generalized by the Tup polynomial, both important structures in algebraic graph theory. Kemp had already known of and drawn attention to non-planar case in 1879, and many results on the generalization of a planar graph coloring to surfaces of higher order pushed into the early 20th century. Claude Berg in the year 1960 formulated another conjecture about graph coloring, which is known as the strong perfect conjecture, which is influenced and motivated by the information theoretic concept zero error capacity of a graph postulated by Claude Shannon. The conjecture went unsolved for 40 years until 2002, when Chodnovsky, Robertson, Seymour, and Thomas established the celebrated strong perfect graph theorem. And since the 70s, graph coloring has been studied as an algorithmic problem, as opposed to a functionality problem. The chromatic number problem has been one of Karp's 21 MP completes from 1972, which are a set of computational problems that can be solved by a restricted class of brute force search algorithms. Around the same time, several exponential time algorithms were developed based on backtracking and deletion and contraction recurrence of Zavoky in 1949. Starting in 1949. In 1981, a major application of graph coloring was used for register allocation of code compilers. This is the process of assigning large number of target program variables into a small number of CPU registers. This is a big deal, able to speed up computing times quite a bit, as well as allow for more complex, higher order language. There are several algorithms that work to color graph for use in applied functions in everyday usage, like register allocation. Many attempts to make an efficient algorithm have failed in the process, as it keeps falling into the NP-complete algorithm problem. There exist many approximating problems to solve the chromatic number problem. One such algorithm is the greedy algorithm, which does not guarantee a minimum use of different colors k, but instead guarantees an upper bound, such that the algorithm never uses more than d plus 1, d being the degree, or largest degree, of the graph, which is the largest number of connecting edges to one node. And it promises to have no more than that plus 1. The algorithm starts by picking the first vertex of the set V of G, which is the vertex set, and then it picks the first color that you would have in some sort of order. The algorithm starts by picking the first vertex. Then the following v minus 1 vertices, you must consider the previously picked color and the lowest order color to be used, and not used on the previously colored vertices adjacent to it. If all previously used colors appear on the vertices adjacent to your current vertex, assign a new color not used on the graph to it. This is an order-dependent process, as depending on which order you pick, you could yield something different, like the gamma of G or D plus 1, somewhere in between. An example below is of this. The top graph here only takes 3 colors because you start 1 and go across. The second graph takes these two nodes here, 3 and 4, and switches them so they go in a different order. And because of this, it takes 4 colors to finish the graph. This has led to separate supporting algorithms in choosing the order of the vertices to help obtain a chromatic number instead of d plus 1. Several other algorithms exist to tackle the coloring of a graph. Polynomial time is seeing if a graph can be colored with two colors by seeing if it is a bipartite graph through the use of breadth-first search or depth-first search, which is computed in linear time, which you will get at O of n initially on that. The exact algorithm is a brute force search for the k coloring and considers each k of n assignment, so that's the number of colors to the n power or number of vertices. For colors n, check for each if it's legal, which is impractical for all but the smallest graphs when determining Chromatic numbers, because you're dealing with very large node graphs when you're in certain locations, especially if you're doing like face mapping. Contraction takes two vertices u and v of a graph G such that it is G over uv, removing any edges between them, and remaining edges originally incident to u or v are incident to their identification. In deletion and addition, you just take the two edges uv and subtract it out. They're gone. Usually they would have an edge connecting them, so it would be u edge to v, and all other edges leading to them will be deleted or leading away. Same thing with addition. You would add it in, and then you'd see and you would add in all combinations of edges to those two from the previously existing nodes. And it is done so recursively. It can be seen as the graph of gamma of g equals the min of the gamma of g plus the edge of uv, or the gamma of the contraction of g. Oh, sorry. P is a number of possible proper colorings. This plays a pivotal role in the deletion contraction algorithm, which forms many graph coloring algorithms and plays a major role in the analysis. Applications. Applications of vertex coloring have several categories, such as scheduling problems. In the cleanest possible form, a set of jobs need to be assigned to time slots. Each job requires one slot. This is an unordered problem. However, pairs of jobs may be in conflict with each other, and they do not have to be assigned a time. They don't have an assigned time slot, or because they have a share resources. The graph will have a vertex for every job and an edge for every conflicting pair of jobs. The chromatic number of the graph is exactly the smallest optimal time to finish all jobs without conflicts. The details of the scheduling determine the structure of the graph, such as an aircraft flight times that can be seen as an interval graph and easy to use. And here's an example of such a graph. Right here. As you can see, it is the intervals on top, and every interval that overlaps another interval there forms an edge between it, as the intervals are turned into the nodes themselves. Computers are one of the biggest beneficiaries of graph coloring in the form of their compiler, which is a program that translates one computer programming language into another, i.e., something like the higher level order language like Java gets translated into machine language so that the processor can use it, or machine learning algorithms, and so on. It is used to improve the execution times of the given code, with one of the techniques of the compiler optimization being register allocation, where the node of used values are kept in the fast processor register. And here is a input slot of all the overarching variables. And then there's a creation of the graph based on the variables, and then coloring. So you'd only need to use two registers to keep all the values in. A problem involving graph coloring is what was mentioned earlier, is scheduling. Let's say there are 5 time slots each day, Monday, Wednesday, Tuesday, and Friday, from 9 a.m. to 2 p.m. for final examination. But however, in the testing building, there is this conflict between the classes at the same time of one of those the time slots listed, such that there's a conflict between Math 11, 111, and CS 111, Math 111, and CS 14. CS 14 and 111 Bio 101 and Math 18, Bio 101, 101 and CS 114, Math 118 and CS 114, Math 118 and Math 111. And you would make a graph based on the number of conflicts, and you call that graph S. And then you determine the chromatic number of S. Well, first, you would have to draw the graph, which you would get right here, which is just a pentagram graph with two interconnecting edges, right here. And so then you determine, by starting at one of the nodes, what color you choose. And I chose orange, green, purple, and a couple other colors I had in the waiting list. However, I only needed 3 colors, as can be seen here with the circled graph. I needed green for these 2 nodes right here. Oh, orange, green, green, and purple on the triangle portion pointing out. And this would give us a chromatic number, or gamma, of S equals to 3. And that would be one of the problem-solving aspects of it. So then what does that chromatic number translate into? It translates into you only need 3 times to have the test taking, so that you have no conflicts between any of the other classes in the building, as they don't share resources. And then here is a picture of a flight manifest problem in the algorithm, and I don't know how to do elegant screen recording, so here we go. Alright, thank you for watching my presentation.